Now I want to talk about the IEEE 754 single precision floating point notation. This is, so the IEEE 754 floating point notation is what most modern CPUs use to represent floating point numbers. So this is an important one to understand. So first of all, this is, if we go back to the 8-bit floating point notation, remember we had a sign bit, we had exponent bits, and we had mantissa bits. So we have the same thing with this IEEE 754. So we have a sign bit, and we have 8 bits to represent our exponent. And notice how this is using bias 127. So what that means is that we've taken our exponent and added 127 to it and then converted that to binary. So for instance, if let's say our exponent is 3, we've taken 3 plus 127, and that's equal to 130. So this 8-bit exponent is, so the exponent that we're going to put in this 8-bit, the exponent that we're going to put in for the 8-bit exponent that we're going to put in is going to be written with this bias 127 notation. And then we have 23 bits to represent a 24-bit mantissa. And so this 24, we're representing the 24 bits with 23 bits, because if we go back to the scientific notation, so let's say we have 1.1010110 times 2 to the third. Remember that if we have our number written in scientific notation, we can assume that this is always going to be 1. So if we know what that is, we know it's always going to be 1, we don't need to put it in our number like if we put it in our number, we would basically be wasting a bit because we already know what it is. So the only part of the mantissa that we're going to be putting into this floating point number up here is the part of the mantissa that comes after the radix point. And so by doing that, we can represent a 24-bit mantissa with only 23 bits. So we have so we're going to always assume, we're just always going to assume that this bit before, or the number before the radix point will always be 1. And so the way that we convert numbers into this IEEE 754 floating point notation is, first of all, we look at our number and we look at, okay, is it a negative number or is it a positive number? If it's a negative number, we're going to put 1 in for the sign bit, so that would be here. And if it's a positive number, we're going to put 0 in for the sign bit. The next thing we're going to do is convert the decimal number to binary. So whatever number we have in decimal, we're going to convert that to binary. And once we do that, we're going to convert the binary number to scientific notation. So it would end up looking something like this, like just depending on what number we have. So basically we want to get our number written in a form like this. So this is scientific notation. Then what we're going to do is we're going to convert the exponent using this bias 127 notation and write that in binary. So for instance, if I look at this number that I just wrote down, I have 6 for the exponent. So I'd have 6 plus 127, which is equal to 133. And so then I would write the 133 as a binary number. So I would convert the 133 from base 10 to binary. so to base 2. And then this is what is going to go into this exponent. And then last, you have everything, so you're going to fill in the sign bit. So that's going to be a 0 or a 1 right here. You're going to fill in the exponent, so that's going to be whatever you got here. And you're going to fill in the mantissa, so remember that's going to be this part of the mantissa, because we're going to assume this is always 1. So that's the method for converting a number into the IEEE 754 floating point notation. And next time we're going to practice doing this. So next time we're going to convert this 194.375 into the IEEE 754 single precision floating point notation. So if you want to practice doing this ahead of time, we're going to do this next time.